Hi, so we're going to talk about the advection dispersion equation for non-reactive solvents today. So what we're looking at is a representative elemental volume. That was the REV, and so here's my little block of it. You know, you've got stuff coming in and going out of your block here. And so when we look at transport of solutes, we're looking at advection plus mechanical dispersion, and we've already talked about that, plus diffusion, which we talked about, diffusion. And so these two together are what are referred to as hydrodynamic dispersion. Hydrodynamic dispersion and stuff like that. So this is advection dispersion equation. So these are the two parts that work out dispersion, is mechanical dispersion and diffusion together. So if we were looking at this, if we looked at advection, solute transport equals the velocity. So this is the average groundwater velocity times our effective porosity times C, which is our solute concentration, over a cross-sectional area of our representative elemental volume, so a cross-sectional volume over that. This will equal Q, which is our fluid flux. That's the Darcian fluid flux times the concentration times the area inside of there. So this is our specific discharge, the change in our concentration over a cross-sectional area inside of there. So this is cross-sectional area. Ooh, that should be an A instead of an X. Cross-sectional area inside of there. So that is the average behavior of a solute inside of there. Now, if we did dispersion of a solute, transport, that equals the porosity, the effective porosity, times the coefficient of hydrodynamic dispersion, times the change in the concentration over the change in the area, and then the change in the area over in here. And so this is dispersion and this is advection. So the total of these two, because we're looking at the advection dispersion equation together, so the total mass of solute transport in the nth direction, so whatever direction the groundwater is flowing, per unit area, so that's one area that's over here, per unit time. Okay, so a lot of this is dependent on your aquifer. So if we look at this, we get the steady state condition, F at some direction equals the velocity times the effective porosity, C, so this is our advection part of it, minus the effective porosity, our diffusivity, and our change in concentration over in the direction. This is our dispersion part of it. This negative sign here indicates that dispersion is from an area of high concentration to low area of concentration. So if it was plus, it would go the opposite, which doesn't make any sense. So when we look at this, this is for steady state conditions inside of here. You know, this is flow that happens into there, and this is our continuous, our steady state conditions. So steady state conditions that happen in there. Now, if we apply this continuity principle to solute transfer through our representative elemental volume. Now, there is conservation of mass, so what comes in has to come out or is stuck behind, but we don't lose it. We'll get to that shortly when we start getting into when we actually see solutes actually disappearing, where they're being transformed. That's the next section after we get through this. So the change in solute flux through a representative elemental volume, so as it's going through here and it's coming out over here, that change in solute is the change in the storage. So it's being stored inside of here. And so when we look at that equation, what's going on? Well, so when we look at that change in so this is the change in the solute flux through a representative elemental volume equals the change in storage. So our flux in the x direction plus our flux in the y direction plus our flux in the z direction, change in z, equals negative of our effective porosity over the change in concentration over the change in time. Now we're going to substitute equation 1. So that is this right here. This is equation 1. And we're going to substitute equation 1 into, this is our equation 2 in here. And then when we do all of that, we end up with the change in x, our velocity in x minus our concentration, known as our dispersion, in the x direction with time, plus our y direction, the velocity in the y direction, the concentration over the dispersion in the y direction, plus concentration in the z direction, change of velocity of z, concentration, change in concentration over constant time, equals the change in concentration over the change in time. And in one dimension, so if we're dealing with one dimension, this simplifies, this whole equation simplifies to dl, which is our hydrodynamic dispersion in one dimension, over, if we take minus the velocity, change in concentration over change in x, equals the change in concentration over change in time. So this is our advection dispersion equation. So the ADE in one-dimensional case for steady state flow. So if we were going to go to 2 and 3D, we'd have to include the term, the dispersion in T, which represents the transverse. Note that a 3D case, the dispersivity in the transverse is often not equal to the vertical, and so we have to get that into there. So the dispersion equation, this is our advection dispersion equation in one dimension steady state, and we're dealing with that. So if we look at mechanical dispersion dominated systems versus diffusion dominated systems, so we talked about what mechanical dispersion was and diffusion dominated systems were, and so we're going to look at the differences between those two systems in there. So if we look at the dispersion equals alpha and L plus D, and we look at T equals alpha T, velocity on the T plus dispersion. At high flow velocities, this alpha and velocity term dominates. So at very high systems, we're going to have that, the dispersion and the velocity that we talked about. But what about at low velocities? So where this becomes dominant, where we talk about diffusion, because once the flow is so slow or non-existent, we're going to be looking at more dispersion. And so what we end up looking at is what's called a Peclet number. So the Peclet number, or PE, is a dimensionless coefficient related to the effectiveness of the advection dispersion transport to diffusive transport. So again, the Peclet number, it's dimensionless, so we don't have to write anything with that. It's a dimensionless coefficient relating the effectiveness of the advection dispersion transport to diffusive transport. Okay, so our Peclet number equals the velocity times d, which is our characteristic of flow from our porous media. Usually this is the average diameter of the grain in there, over dd, which is our free water diffusion coefficient. And this is our average velocity in here. So what you're looking at is, I've used Peclet numbers in some things where we want to really look at how diffusion is affecting the system, especially in very low flow systems. So we have the Peclet number. So we look at the average velocity times the characteristic of flow for the porous media. And so we usually look, this is the characteristic of flow. This is usually the average diameter of a grain in the porous medium. And then this is our free water diffusion coefficient. Okay. And usually we determine Peclet numbers are based on laboratory column experiments where diffusion domination and advection dispersion can be defined. So when we put in, like, we can just put clay and we put the water on top of it, we watch the salt or whatever diffuse into there, we can then look at these things very easily. In a diffusion dominated zone, the DL and the DT are constant and independent of Peclet number, but when the advection dispersion dominated zones dominates it, so these things dominate, they should vary linearly with the Peclet number. So usually the Peclet number will, depending on how fast or how slow it's moving, so if it's a diffusion dominated, very slow flow, Peclet numbers will dominate. If it is fast flow, we're going to get dispersion being the most important factor here. So now we're going to look at solutions to the advection dispersion equation. Okay, so we're going to look at how do we solve for it. We're going to go through some derivations of it. We're going to look at boundary conditions, different types of boundary conditions, and then we're going to look at how we do the modeling of the system. So say we have like a little flow system like right here. So here's our ground, here's our water table, here's our contamination, and the flow is coming out over in here. We have these boundary conditions, so these are no flow boundaries because, you know, the contamination is not going to go this way. You know, flow is only going to happen in this direction, and then the water is all going to discharge over here. So we have these no flow boundary conditions here. And so we know what type of soil we have. We have a nice aquifer system here. We have a low K bedrock here. And we know all of our systems, stuff like that. So we have to understand the flow in order to understand the system, so, you know, understand the geology in order to figure out where the contamination is going to flow. So in order to figure out the flow here, the flow problem, well, first you've got to know what the size and shape of the system is. Size and shape of the system. So, you know, we have to look at, you know, where is it, how big is it, what's our, you know, what are we representing here? And then we have to look at the initial hydrologic boundary conditions. Okay, so these are the hydrologic boundaries. Oops, I could spell hydrologic boundaries. Again, if I could spell the hydrologic boundaries. And so we have two different types of hydrologic boundaries that are conditions that are occurring in here. So type 1, so we have type 1, is where we have a specific head. So we know the constant head boundary. So like here, this is a constant head boundary. We know what the head is along that type of thing. So this is a type 1 boundary condition. So, you know, we know that this is specified head that happens inside of there. So the head equals the head at different locations and different times. And so we know what the head values are. And type 2 boundaries are where we know what the specific flux is. So a flux is over a cross-sectional area, how much is moving in that area. And so here we have a flux. We know the specific flux that's occurring here. So so we have Q equals Q at any location at any time. We know what that is. And so this is like recharge at the boundary conditions inside of there. We also need to know, besides like what the boundary conditions are, so our head and our no flow boundaries, that, you know, we know that the water is going to come in here and here. We know that there's a flux that's going to happen in here. We also have to know too, we need to know, so this is our first thing we need to know. Second thing we need to know is the physical properties of the system. You know, we can do everything we want without knowing the physical parameters of the system. We can estimate, but, you know, things we need to know is like hydraulic conductivity, our effective porosity, the storativity, etc. And then the third thing we need to know is the initial head values inside of the case. So if we know what the initial heads are across this, and then we have a transient conditions, it's changing with time, then we could know that. So for a transient case, we need to know the initial head values inside of the boundary conditions. So we can only model is only as good as what we can measure. So only as best we can understand the system. We know what types of boundary conditions we have. No flow along this bottom here. We know that this right here, groundwater on this side would flow this direction. So we know these are boundary conditions, and this is a no flow boundary. We know what all the system is, and we know the initial head values. Then we can go on and solve for flow. Okay, so now we have then when we solve the flow equation to determine the head distributions, we usually look at it in steady state in one dimension in there. And so we will have all of our heads be equal with the change in time is 0 because we're in a steady state conditions. So we know that our change in head with the change in time, it's not really changing because we're in steady state. It's not a transient condition in there. And then we determine flow velocities from the Darcy equation. So we get our velocity measurements from our specific discharge divided by our effective porosity equals our hydraulic conductivity divided by porosity, the change in head over the change in time, or change in length, sorry. This should be an L, change in length. And so when we look at velocities, we use Darcy's law. We're assuming all the heads are remaining constant, so it's not like they're changing with time because we're having a steady state condition. And then when we look at the transport of this, we identify the source of the contamination. So we're going to be looking at where is the source location here. Have we defined the boundaries, conditions that we're looking into here, and can we say what the initial concentration of the little green specks is in here? And then we can solve the transport equation, determine the concentration distribution at any given time. And so when we do that, we end up with our diffusion in the latitudinal direction, our change in concentration, change in x minus the velocity in the x direction, change in concentration or change in x equals time. So this is the one-dimensional advection dispersion equation for steady state flow. And usually we use the calculated velocity up here and an analytical or numerical model in order to do the rest of the system and stuff like that.